Okay, so in this video, I'm going to try to make it short, but basically I want to show what is the shear effect. You will understand in a few minutes for a cantilever beam. So this is a cantilever beam. Due to that force, this would be the bending moment. So maximum at the root, 0 at the tip, and the force of the shear force is constant. All right. So in order to do that, you know that every time I do something, I like to do validations. So in this case, I have this small MATLAB file that I will upload, not to YouTube, but I will show you where to go and obtain these files, okay? Along with the video at the end of the video. So basically it will be, this is aluminum 2024. This would be the force at the tip, and this is the length, everything in this is inches. And a cross-section on an I-beam, that will be 1 at the top, 1 at the bottom, and a flange of, I think it's 0.1. Anyway, that will be a lot more clear. And basically, here you see that once I run it, the deflection, just due to bending, is 0.6933. The deflection, just due to shear, is 0.00296. So the combined deformation is 0.07229. Okay, so let's see what does that mean. So what does I mean about shear? Okay, so shear, here you see that depending on the cross section, you're always going to have shear. And what happens is that in most cases, the effect of shear is neglected. Okay, but you can see that the shear force, if the force is going down, this force here might have an effect on the total deformation. So not only the external load due to bending, okay, so the bending moment will have an effect, but also the shear. If I close this. All right, so let's do that cross section and see what happens. So file, new, I do the first cases with you, and then I already did this model, so we should save some time because I will just be opening them. So let's say here, I try to do it a bit fast. So the new material, 2024, you see it's 10.7 to the 6, Poisson ratio 0.33. Okay, now geometry curve project points, we say is 10, so 0 to 10. Okay, you can do Control A to recenter. Properties, new, make sure to select the material. And here we're going to go to element property time beam. Okay, so here's where you're going to have to be careful, all right, to fully understand what's going on. So I'll put here shape. You can go, we use an I-beam that we say the top is going to be 1 inch, the total height is going to be 1 inch. So height 1. Width top 1, width top bottom, and the thickness of each one will be 0.1, 0.1, 0.1. Now you see here the Y is going up, so in order to make sure that this is going up Y, we're going to say that the direction Y is up. All right? And this calculates the moment of inertia over here, 0.0449, 0.0167. We can go and check if you want later on with the MATLAB as well, but here we go. But here, please pay attention to this over here, computer shear center offset. Okay? Save and cancel. Oops. All right, I think I went too fast by canceling. So let's just do it again. And beam, you go fast, 1, 1, 1, 1, 1, 1. Up, okay, cancel. So the properties over here. Mesh control, size and on curve. Doesn't matter how much we put, let me just put 20. Just for the sake. All right, so now mesh geometry curve, I come over here. All right, the beam property. Remember, we need, this was on the Y direction, so that needs to be changed. And you want to do preview, okay. So here, the best thing to do is that you go to the little cube over here and say thickness cross section. Okay, what happened here? Elements by type, so they are here. Oh, there we go. And you will see over here, okay? We're now deactivate it. Okay, I don't know what happened here. I've never seen that before. So model, load, nodal. So you can put here loading. Let's say this will be the tip. Enter node. So which one is the last node over here? Okay, what happened here to the view? I have no idea. See if I can eliminate this view here. Okay, so let's say we are here. Rebuild, yes. Model, constraint, nodal. So let's say here cantilever. We're going to select this node over here, which means that that one is fixed. Okay, and now we go model, load, nodal, and say force F equal to 100 at the tip. Method ID. Something strange here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it should be 21. Let's see if it gets you to 21. Okay, we don't see it, but minus 100. Okay. All right, so there we go. So file, rebuild, yes. Let us file, save as. So beam shear effect, this already created a model, but I'm just redoing here. So this would be, let's say model, beam. One, save, and let's run it, and let's see what's gonna happen. Again, this should be running, should be a lot faster, but because I'm not running on the computer, I'm running out of the virtual side, is a bit slower, but this should just take about 1 or 2 seconds if you do it on your own computer, meaning setting on your own computer. You can still see this is still pretty fast. All right, you do F5, so you can do contour, deform, form. Let's look at the total translation. And this gives you 0.723. So what does that mean? That means that in this case, once we go to the MATLAB, this will be kind of close to the one, or almost identical to the bending effect, which is 0.0693, plus the shear effect, okay? But most of the time, people don't add the shear effect, they just look at the bending effect. But you see that the FEMAP, by default, will also take into consideration the shear effect. So how not to take into consideration the shear effect? So let's go to this model, file, let's say here, save. Let me just reuse the same one because I'm not going to use it. I'll give you the other files. That way, all results. I mean, we can keep both of them. Let me just change here the element property. So let's see. Edit, shape, change. And the other thing I'm going to do here is to eliminate the compute the shear center offset. All right, so actually, I think it did it, but What I mean is that this is 0 and this is 0. Can leave the perimeter, and J, and OK. File, rebuild, yes. Let me do again here. This would be the same as not, don't select this one, okay? You don't have to select that one. So in that case, this one should just be 2, 0. I don't know why it's not 0 here, but if you want, you can put 0, the shear effect. Okay, again, file, rebuild, yes. And now, if we did everything wrong, what should we get? I mean, if we did everything right, sorry, we should just get the effect due to bending, so close to 0.0693. So this is done. So this should be the second result. And you see we get exactly 0.0693. And this is with both of them, 0.0723. The only difference between these two is that when you run here the element will give you the properties. When you don't have shear effect, these two values should be 0. And when you run the shear effect, these two values will not be 0. Okay? But we're going to take this one step forward. So basically, we know that by definition, the plate elements or the shell elements are good in bending, but are not good in shear. Okay, and similarly, we know that in general, the solid elements are good in shear, but are not very good in bending. Okay, so let's see. Let me just set this one. File, close. Let's say yes. And now what I'm going to do is that I'm going to open. See, it's done here. It should be, that would be the same model we have done here, 1 and 2, no shear factors with shear factors. Beam plates motor RB2, okay, beam plate motor RB3, the motor RB2, RB3, this would be the case of another video, the RB2s RB3, but not in this case. So in this case, what I did is you can see that basically I just recreated the model here. This is the fix. I know this looks like solid, but really should be only 3 surfaces. As you can see over here, 1 surface here at the top, 1 surface at the bottom, and 1 in the middle for the web. So it would be, okay, top, bottom, and the web over here. And I used to put the load, in this case I think it's the RB3, but the RB2 should give you the same thing. So you create an RB2, that's it, okay? I will do that in another video. But here you see that what is the deformation, I already run it, it's only 0.0569. So I will say that plates are good in bending, but not in shear. So basically, you see this one is not that off from it. It's not really good, this model, okay? Modern beam with plates, you see it's not even close only to the bending, and to both effect, it cannot really capture the effect of the shear. All right, so shell is probably the most used element in final element, but you see it's not always the best. And this is one of the cases. So I did the same thing here. I created the same model, but with solids in RB2s, RB3s. And now this one, yes, you should see the whole cross section. Let's see what here. Oops. I think it should be view. Oh, here. Wireframe. No, I didn't do the wireframe. Solid. Anyway, this is what you have here. Again, this will be the deformation, and this time, this is all solid elements. Let's see if we can do this. Yeah, so basically you see this, all the nodes over here. All right, and this is solid. And you see right here that now, when you take solid elements, you can really capture the effect of the shear in addition to the bending. So it's almost like the exact 0.0729. It was 0.07229. Okay, so it's pretty close. And it's also pretty close to the result just using the beam. All right, so again, if you want some additional information on the shear effect, all right, I think I can put this folder here. I will put all these files. I will tell you where, but you see deflection due to shear. I got this stuff from online. Okay, that's pretty strange. You see this is from the U.S. Department of Agriculture, but actually it's pretty good document. This is the strain energy. I'm not going to get into detail due to shear. Then using something called, probably it's mentioned here, the Castellano theorem. Anyway, blah, blah, blah. You can go through this document. They tell you what is the expression for the deformation due to shear. All right. So I would put that one, and then the shear factor K, how to find it. Here is another document that gives you an example on how to do it. All right, it's not bad. And this is the file that I use in order to create the solid that was done in CATIA. I don't know if I will put that one. This is from one of my lectures. This is a bit more complicated structure. The only beam is one is a beam, but built of different panels. Okay. And basically in this case would be some bending due to the force V over here, but also some of the shear going through 3, 4, 2, 5, and 1, 6. And you see here these two expressions. This is the bending expression. Q is the bending, total deformation. This is the expression due to the bending that is induced by the bending moment. And this is the bending due to shear, which in this case is induced by the shear flow. So you see, this is same the case we have. The V force will be constant. Okay, the bending moment is maximum at the root, 0 at the tip. Anyway, this is a lot more complicated problem. Will be good to validate it, but it's not the case here. But basically at the end you see that the deformation just due to bending is okay, so right here it's at the end 21.17, but if you add the deformation due to shear, you get 2.54 additional one. Okay. All right, so obviously you will have this video on YouTube, but if I will also put the files in a website. That is actually this one here, FEMAP.com. And here basically you see already have some videos. And if you open these ones, so let's see, that one looks like not having files, but I know I did one of them. Okay, you see this one, if you open the support files, RB2, and you download them, you will have all the different models that I use in this video. I'm going to do the same thing for the video I just created. So you go to this website, in addition to the video, you will also have the supporting files. All right. So again, there's a lot more to say about this video, but I definitely don't want to make it too long. And if you have questions about the RB2, RB3, I will probably be creating a new video about showing you the difference between the RB2 and RB3. All right. Thank you for your attention.